Okay, folks, it is 5 minutes past 11 on my watch at this point, and I'm going to reconvene our seminar. I hope that you all had a nice restful break and that you're ready for some really exciting material now. Again, my name is Jeff Rosen. I'm the program manager of the Wvtap team. I'm also a statistician, and I've been designing large-scale monitoring programs for many years. I'm going to try and make this of interest. This is a very important topic. It's one of the main reasons that we did the 10-home sampling, and hopefully this will be informative and useful for you. One thing I want to emphasize is that the plan that I'm going to give you today is partial. It's based strictly on the information that we have from the 10-home sampling. The final sampling plan will be very dependent on the results that we get from the health effects expert panel, so we can't give you a final design today. There are also some considerations and some questions that we'll be discussing that need to be considered before we finalize this plan. So with that, I'm going to get started. I'm going to time myself, try and do that well, get myself to sit down on time, and we'll jump right into the presentation. So in a perfect world, what would we do? If we wanted to understand the concentration of MCHM that we have in people's homes and in residences, etc., throughout the 9 counties that were affected by this spill, we would go out and we would sample every single home and every single business. The numbers that I have here are strictly from the homes. West Virginia American estimates that there are 86,866 residential customers affected by the MCHM spill. Sampling every single one of those homes at the same level that we did for the 10-home sampling would cost somewhere around $635 million. I think everybody can see that it's unlikely that that's going to happen. But the thing is that we can do a sampling program which will get us similar level of knowledge. It won't give us the perfect, what we call a census of the data, but it will give us a good estimate based on some of the sampling. Just so that we put this in some kind of context, if we were to try to sample all of those homes, we would need about 100 teams of 3 trained people each, working for 86 weeks to complete the sampling. And you can imagine the amount of logistics and the shipping and the number of bottles and the amount of work that it would take a chemistry laboratory would be astronomical. So clearly we're not going to do that, but what we're going to describe and we're going to ask some questions is how do we sample for this? So that everybody's familiar with sampling. We can estimate things pretty well by doing a sample rather than by doing a census and sampling every single unit that we have a question about. So what is our sampling frame? We have 9 counties that were affected. We have 21 pressure zones that were affected. And we have as many as 6 different locations within the home that we might want to sample. Remember that in the Wvtap sampling program, the 10-home samples, we sampled at 4 locations. We'll talk further about that. The likelihood is that if we want to do a thorough sampling, we would sample at the intake to the home, so at the point where the water pipe comes in to your meter at your house. We also would sample some of the external spigots around the house so that we get a better feeling of the overall concentrations. So a recap of the pilot sampling study, because again, the reason this was done to some degree was for us to understand the variability and be able to design the larger sampling program. Why did we collect the data? We needed it for this full-scale sampling effort. We sampled 10 homes, 4 locations per home. 3 replicate samples were taken per location, and that was done for each laboratory. So we had 2 laboratories, each of them got 3 samples from each location in the home. That gives us an understanding of the variability that we might see. When we were doing our sampling of 10 homes, we did 3 analytes for each one of these samples that were collected. Some of the key findings. One of the laboratories detected lower levels than the other. It's very important in this kind of a program, Dr. Welton mentioned this earlier, that we specify what the detection limits are that we require of the laboratories. One of the laboratories was working at a higher detection limit. Because of that, we got virtually no hits of MCHM at that one laboratory. The other laboratory was working at a much lower detection limit, and there we got the majority of the samples were positive. I believe we had a total of 10 samples that had non-detects. PPH was not present at all. That was a big concern for many people early on. I think we demonstrated, at least for these 10 homes, that we're not seeing PPH. And MCHM, when present, was at concentrations below the screening level of 10 parts per billion. So you've heard all this before. This was meant to be a recap. Further, we sampled that in the kitchen at cold and hot, in the bathroom at cold and hot. All the concentrations of MCHM were low. This is very important. Dr. Welton mentioned this earlier. There is variability. That means spread in the results between the different locations within each home, but there are no clear patterns. There was a supposition early on. Many people believed that if you were to sample the hot water, you would get higher numbers than you would in the cold water. We actually found the opposite in general, that the cold water was higher, but again, the patterns are not well established, and based on that, we believe that there's variability within each home, and it depends on the home itself. There are some statistical differences between hot and cold water in the kitchens versus the bathrooms, and then hot versus cold taps, but no clear patterns, and that's very important, because if there were clear patterns, then we would need to design the sampling plan to attend to those patterns. We would need to make sure that we got samples at all of these different locations. Okay, so here's a really nice summary that we have of the results. Here are the house numbers along this axis, and this is the MCHM concentrations, and these are strictly from the Eurofins laboratory that was working at the lower detection limits. As you can see up here, we've got the different colors, so you can see which of the locations have the highest concentration. So for example, I believe tub cold is the green, and you can see highs there. The kitchen cold is, can't quite see these colors, excuse me. So the kitchen cold are the red dots, and you can see in some cases they come out higher. The general variability amongst these different samples is fairly tight in most of the samples. Clearly in house 8, where we've got higher concentrations, we've got much more variability, and we'll speak to this variability right here as we do the design. There are a couple of other homes that have a little bit more variability, but keep in mind that the concentrations that we're looking at right here are really quite low. So the variability is not very high. It may be high relative to the mean, but it's not very high relative to the concentrations that we're looking at. So this is an important finding, and this will factor into our design. So the differences between the locations and the homes, again, there are statistical differences, but no patterns. The differences at most of the locations are very small amongst those 3 samples that we took at each location. We did observe real variability. That means these results are not exactly the same. And again, as Dr. McGuire mentioned earlier, it supports what we've heard from the people in West Virginia, and that is that they smell, the concentrations seem to be different. They're getting different odor characterization at different times and within different locations within their homes. We clearly do see that overall over the 10 homes, the highest values in each home are the cold water bathtub for many of the homes. And because of the general lack of a pattern, it would be best to take locations at multiple locations in the home so that we get an overall average concentration for the home. That would be a good estimate. So one of the things, and Dr. McGuire, who raised his hand so enthusiastically earlier when I told you how boring statistics was, is a big fan of this slide, because this is something that I've spent my career trying to get across to people who are studying statistics. This is the key. Statistics is all about the questions that you ask. The design of your experiments, how you analyze the data, what data you actually collect is all about the questions. Ask a different question, you'll do a different analysis, you might collect different samples. So we have many questions. I'm sure that everybody in this room has got questions, and we can make a long list of them. But the 2 that we will focus on for the design of the large-scale sampling is, how confident can I be that the water in my house is less than the screening level? Whatever that screening level turns out to be, that's an important question. The second question that I'm going to address is, what percentage of the homes are below any particular concentration, and including a safety factor in here? These are 2 different questions. This question is about your home. This question is about what are the concentrations in individual homes. This question is more of a management question, and asks the question, how many homes and what percentage of the homes over the entire area have levels that I might be concerned about. Not that I am concerned about, but that I might be concerned about. So let's dive into these two questions. For question number one, is the concentration in my house less than screening level? How many samples do we need to be taken within each home? This is an important thing. Let's say I take one sample. I have very little understanding about the variability. If I took another sample, maybe it would be very different. If I took 100 samples, I would have a much better understanding about the distribution and the variability of those results. But the question is, once I have 100 samples, do I need 1,000 samples? The answer is that you reach a point of diminishing returns. You take more samples, you're not really going to learn all that much more with 1,000 samples than you will with 100 samples. Of course, the variability will tighten down mathematically, but I'm not sure how much that means. So the point is that there's a balance point, and we need to strike that balance point. We are going to use a technique called power analysis to determine the number of samples necessary to have a 95% confidence interval. That means that when you have a mean, we're going to tell you what the bounds of that are, and we will be 95% confident that the real number in the house falls between those values. Power analysis is a very effective way to relate the sample size and how many samples I'm taking to the variability. How much variability do I have in my samples, and the differences that are meaningful. I'll get back to this and I'll explain this to you in a minute. This is very important. Okay, so this method that I'm going to show you today, called power analysis, is an elegant way. If you're a statistician and a geek like me, you would look at this equation and you say, this is a thing of beauty. Whoever first put this together did something really valuable for the community, and certainly for geeks like me. So let's set up the power analysis. I told you there are 4 things we need. What are the differences that we're trying to detect? What is the range of the variability we expect to see? What is the confidence interval? And I'm going to set that at 95%. That's the answer to that question. And then the power of the test is to the ability to detect real differences when they exist. I'm going to set that to 80%. Those 2 numbers are set. The only 2 that we need to establish above that are numbers 1 and 2. And I'm about halfway through my presentation. So what is our level of concern? This is how I'm going to define what that difference is that we care about. What number do we care about? 10 ppb is the screening level that we have right now. It will be reevaluated later on in the week. That's part of the reason I can't finalize this. We want to be able to say that an average observed in the home is less than 10 ppb with 95% confidence interval. That should give you guys some comfort. The concentration in my home is less than the screening value, and I can be sure of that number with 95% confidence interval. The highest means that we observed in the 10-home sampling, as Dr. Welton told you before, was 4.4. The highest concentration that we observed is 6.1, and as I've been telling my team, my experience over doing this for 39 years is that we go out and take some more samples. Eventually we'll probably get some numbers that are higher than this, possibly not very much higher than it. But right now we're in a situation where our highest value is 6. The level that we're concerned about is 10. So 10 minus 6, I believe the answer is 4? 4. 4, good answer, McGuire. Thank you very much. So what we're looking for then is that we want to be able to detect a difference of about 4 parts per billion. Now 4 it would be much harder if the answer is that we're trying to detect a difference of 0.4. We would need a lot more samples. It's easy to detect things that are far away and say they're different than it is to detect things that are close and say that they're different. Okay? Easier to detect big differences than little differences. And what is the level of variability? Well, the highest standard deviation that we observed in a home was 1.4 parts per billion. The next highest was 0.5, so these are not normally distributed. It jumps up, and the lowest value that we observed is 0.13. The range of variability we need to deal with is 0.13 to 1.4, and you're going to see that I'm going to show you that range to be exact. And here we are. Here's the picture of elegance from a statistician's perspective. This is the power analysis curves. It relates the number of samples that we are taking to the differences that can be detected with this 95% confidence that we have. And here are the different standard deviations. I varied it from the numbers that we spoke about. What is the level that we care about? It's 4, it's right across here. At the levels of the standard deviations that we looked at, if we look at a difference of about 4 with the worst case scenario of the standard deviation, it's about 2 samples. That's all we need from a statistical perspective. We take 2 samples within each home. we will likely be able to detect differences of about 4. I'm going to probably design the final analysis, that number to be a little bit different, because I want to make sure that we have a level of safety in our design. So with that, the tentative suggestions for the sampling program, for a larger sampling program, would be minimum of 2 samples, 1 each in kitchen cold and tub cold, because again, those are the highest values. Benefit will be that we'll continue to have an estimate of the house concentration overall, and we'll continue to understand a little bit about the variability. I would feel more comfortable with 3 samples per home, just because I have a safety factor. It gives me a little bit more information. 2 that feels a little bit low, but again, statistically 2 would be fine. How many homes in each pressure zone? The variability spread in the MCHM concentrations among the homes in the study was fairly low, with the exception of house number 8. The overall average concentration of MCHM in the homes, 10 homes that we studied, was 1.4 ppb. This is an important number, okay? 10 homes that we sampled, numbers are pretty low. Standard error of the mean, which means the standard deviation of the averages, was 0.3, about 0.4.